right. Y'all, we're finishing module 8. We're on 8B. Well, actually, I'm going to send a quiz home with you today to take home, right? Because we're going to finish talking about this, then you'll have a quiz, and next week, what's happening next week? Midterm exam, right? You're going to come in and sit down and take the exam. And you're done. Yes?
Is there anything we can do to get extra points?
Yes, you can do that STEM week. That STEM week that we have, the week after, yeah, we can do a science fair project.
Does that add points to our midterm?
It'll add points to wherever you need it.
Oh, sweet.
Okay? Yeah, so I'll add the points to wherever. All right? But it is actually kind of required because we have a whole day set aside for it.
I'm already doing it.
Good. Glad to hear it.
I don't have to
And
do
you
more
can take it to the big one if you want. The big show in January in Austin. No, it's actually in Kyle.
It's not
Yeah.
that great.
I sent you all the information, right?
Kyle?
It's in Kyle.
pretty far
Yeah.
I live in Kyle.
There you go. You should do
You
it,
do
John.
in Kyle?
I really don't want to.
But you have to do it for this class anyway.
Wait, I have to go there?
No. You have to do the project for this class.
So
Well,
you have
you
You
to
don't
Okay.
have to take it to the thing in Kyle. But if you do take it to the thing in Kyle, you could advance past there and take it to something in Austin.
Could I get extra credit?
Yes, definitely. No question. All right, so you'll get some credit here in class for it, and then if you take it to to the big one in Kyle, you'll get even other extra credit. Okay? Got it? All right. So we're going to finish up 8 here. So that means the midterm is going to cover modules 1 through 8. All right, so the best thing to study are corrected quizzes. If you're doing the test at home, go through those. Just go through your book, your lab book, and remember some of the labs we did. Sometimes it'll say, remember in the lab when you did la 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 la? Well, just look through it and get re-familiarize yourself with those labs that we did. All right, so right now we're talking about work, and we're going to look at what work is in a scientific sense, in a physics sense, versus what we think about work. But before we get to that, we're going to take a quick look at those things we just mentioned at the end of last lecture, those different kinds of energy. For instance, thermal energy, electrical energy, chemical energy, electromagnetic energy, sound energy, and nuclear energy. All right, so we're just going to kind of breeze through these a little bit because there's just a little bit in the book on this for you. I'd like you to know it, though, for quizzes and tests. Although I did not write the quiz, and I forgot to, I have it, but I forgot to look through it to make sure. Sometimes I have to change some things if we didn't do an experiment or something like that. So I'll check it before I give it to you. All right, thermal energy. So my little granddaughter, she's 3.5 years old, and she was helping me pick out pictures, and she told me to pick this one with the dog, even though it's a little bit creepy. Yeah. So, what is thermal energy? It's the total kinetic, remember what kinetic means? Kinetic means it's moving, right? It's moving. The total kinetic energy of the moving atoms and molecules that an object makes up, and that's what's called thermal energy. Okay, so the total kinetic energy. We know right now that everything that's made up of matter has motion in it, right? These paper towels. Is there motion in these?
Yes.
Where's the motion?
Molecules.
Yeah. What's in motion? What's moving?
The molecules.
What part of it?
Oh.
The what?
The electrons.
Electrons are spinning around it, right? In an orbit. Yes? That's moving all the time. So even if something is completely still, or we could say this table is frozen. It's in a solid state. That's all frozen means. We think of it as being cold, but that's only because water, to be frozen, has to be cold. But this table's frozen, but is there still motion happening in here? Absolutely. Those electrons are spinning. It has potential, but it also has thermal energy. Okay? Now, things like this dog who's alive, people who are alive, our thermal energy is something we can measure. We can measure it because of the amount of heat that's coming off of it. So you can kind of think of thermal as being heat, but at the same time, keep in mind anything that's got any motion going on it has thermal energy. It's just the thermal energy of this table is very low, whereas the thermal energy of me is higher. You get it?
Yeah.
So we shine one of those night vision camera things on this little dog, and tell me what's the warmest part of this dog?
The eyes and the mouth.
Yeah, now I understand the mouth, right? Because that's how a dog cools down. They don't have any sweat glands. They don't sweat. To cool down, they pant. That's why dogs do that. So I can see how the mouth, but why are his eyes so warm?
Because they're around so much.
they're just kind of creeping me out. I don't know the answer. Also, notice the
Our eyes
ears
are
a little
warm.
bit too, open to the outside, that kind of thing.
Our eyes are warm.
Yeah, so I know that when you take a picture of somebody, the eyes will glow, but it's only because the light's bouncing off the back of the retina there. It's reflecting.
Maybe it's the light energy that
Yeah.
that's getting.
So I just find that interesting. Yeah. So you've seen night vision goggles and things like this, right? That people use, and they can see if a body is somewhere because they're putting off that heat, right? That thermal energy, and so they can see them in the distance. I know some people. We had in my neighborhood, we had a kid, a little kid who was mentally challenged, and he went missing. And they brought out a helicopter and used night vision and found him. He was hiding under a tree, and they found him because he was glowing a little bit.
Mhm.
So they were fun. So it's really great technology. And is that it? I thought there was a point to that. Okay. Next, chemical energy. Chemical energy is energy stored up in the chemical bonds. We've actually talked about that during our chemistry modules. That was, I think perhaps y'all might agree with me, those were the hardest modules we've studied so far, yes? Remember, some of that's going to be on the midterm, okay? I do believe the midterm is completely multiple choice. So that's helpful, right? Okay, stored up in the chemical bonds of molecules that make up a substance. The reason why I put this picture in there, those are different salts that are they're on fire, and they'll put off different colors, different color spectra. You know, so we talked, remember we looked at the spectroscope and saw like different light sources had different types of spectra. Well, these chemicals all give up a signature spectrum. And that's why I wanted to put this picture on there. My chemistry class, we actually do this experiment and burn some salts. Okay, electrical energy. Electrical energy is the energy associated with moving charged particles. Yes?
Is the midterm worth anything more than like the other tests?
It's not worth as much.
It's not worth it.
In the end, midterm plus final is 10%, meaning they're each 5%. But at the beginning, before you've taken the final, it looks like it's worth 10%. But it's really only worth 5. But it only takes that into account when the final is put in.
So why do we do it?
What do you mean, why do we do it? So you can assess the knowledge you have so far in the year. Yeah. It's one of those things that makes this a real course. Yes?
My mom, I did all the tests, like I caught all up to them, but my mom doesn't know how to grade them.
Oh, there's
So-
no answer sheet in there somewhere? There's no key? There should be a key somewhere.
I think there is, but she doesn't know like how to put a grade on it. Like,
You just figure out what each
question's
one's worth.
5.
Well, it depends on how many questions there are.
Well,
I
there's
know
always
if
20
they
on
would
the
just have
test.
10 questions or
There's
20 questions and make it easy for the math. So first thing you have to do is find out how much is each one worth.
yeah.
Which one's
It usually
the
says.
test
Does
is,
it? I haven't looked at them.
each test only has 20 questions on it.
No, you something like 16 or like something.
Are they always right at 20?
I think
If they're right at 20, then they're worth 5
I'm
points.
pretty sure they're always right at 20.
Well, one thing
That's
is
easy
that
math.
sometimes they put the questions into part like
Oh, A, B, C, D. Yeah. Oh, okay.
Those
Yeah.
are more points.
So I would go and count every blank to be filled in. That's how I do your quizzes. Divide that by 100 and find out how much each blank is worth. That's how I do it, John. If she
Okay.
wants to send me an email,
Okay.
you know, I can maybe give her some advice on that. Okay, so we're going to actually cover electrical energy in its own module coming up soon after the midterm, so the second semester-ish. You know, we're already in the second semester now, but so we'll learn more about this. Keep in mind, though, we're looking at energy, and it talks about the flow of electrons. So right here, what we have is we have electrons flowing through. In order for this to happen, there has to be something that drives them, that pushes them. And here in this case, the thing that's pushing them is a battery. Okay, once the battery, which has chemicals in it, so it takes chemical energy and translates it into electrical energy. It can send it through a wire, which will go through up this wire in the light bulb, and that little wire in the light bulb will resist the energy coming through it. That means it's going to try to stop it. So it slows it down. And when it slows it down, it causes it to pile up and it glows. And that's how we get light out of a light bulb. Okay, so that's how it works, by resistance. Now, if that little filament right there inside the light bulb breaks, what happens?
the light bulb goes out.
It goes out. It doesn't light up anymore. The same thing would happen if I removed this wire from one part of the battery. If I took the wire down, we call that an open circuit. It stops. All right, it has to be a closed circuit. Everything has to be connected. The circle has to be completely connected in order for the electricity, for the electrons to move. And they must be moving in order to light up the light bulb. So you see why it's called energy, right? Because it's moving. Also, we could call it work. Remember, work is to move something, right? So we have work going on here. All right, so I I'm considering what to do for our lab today. I thought, oh, we could do some electrical stuff. Well, I can't. We'll do a little something today on that because we have a whole unit on it, and it'll be fun. We have a whole module on it, so we'll cover it later. Electromagnetic energy. I believe we also have a module on this. Okay. Electromagnetic energy. You see the words electric in there, yes, and magnetic, right? So it's associated with that energy, electricity energy I just talked to you about, bless you. It turns out when electricity flows, like it did through that light bulb, that little wire, if you brought a compass up to that little wire, it would make the compass spin around. Because how does a compass operate?
With
Magnetism.
With the poles.
So it turns out electricity, in fact, that's how they discovered that electricity and magnetism were related. There was a scientist who had a compass nearby, and he noticed it was spinning around when he turned the light on, and he said, what's happening? And he realized electricity and magnetism are related to one another. But electromagnetic spectrum is even more than that. We call it the EM spectrum. And it is the form of energy that's reflected or emitted from objects and travels through space in the form of waves. It includes everything. Everything you see, light, visible light, infrared light, UV light, microwaves, yes, the ones that cook popcorn in a little box in the kitchen. Those are microwaves that are part of the EM spectrum. There's magnets associated with that too. And onto gamma waves and X-rays and radio waves and TV waves. Wi-Fi waves that are hitting us right now. You realize we're being hit by Wi-Fi waves? Anybody have, I have this, my cell phone's on. Guess what? I got waves coming in.
Well,
It's not 5G. 5G scares me. So they say 5G is, the waves are gonna hurt us. I don't know about it. Yes.
Well, guess what? We don't get any service here.
Who doesn't?
I mean, I do.
Sure.
I don't.
Can't get service inside the
They don't give us the password to the internet.
Oh yeah. Well, I'm a teacher, so I have the password. So, all right. So my point is, the electromagnetic spectrum covers everything. In fact, y'all, there's some work being done. This is really weird. That gravity is part of the electromagnetic spectrum. What? Crazy stuff. And it's all because these things, the way light works, the way sound works, the way these things work, the way radio waves work, it's very similar to the way gravity works that we know, because gravity is still a little bit mysterious to us. Yes?
You say that 5G waves are messing with airplanes.
That's what they're saying. So if they're messing with airplanes, they can mess with my brain, right? I mean, some
And
people
they're
say it's gonna scramble your brain. I'm like, well, I don't want that, you know?
And they're electric and magnetic, so.
Well, all of them are, including the Wi-Fi coming in, and the Wi-Fi coming into my phone, and this service coming, that's all electromagnetic. All of it is. So is that light. So is the light from the sun. In fact, I'll bring the sun up. Here's the sun. So the sun is part of the EM spectrum. All right, it's sending out all sorts of electromagnetic waves. We can see some of them. It's a sunny day today. We see them, right? Hallelujah, thank you, God, for the sun. Otherwise, we aren't here. Right? We're not here without our sun.
We see this light.
We see this light. This is coming through. The gas is being excited by electrons running through it. That's part of the electromagnetic spectrum. It happens to be in the part called visible light. I'm going to show you the spectrum here in just a second. But take a look at the sun. The sun is active. Is it moving? Mm-hmm. All the time. Do you see that little stuff spraying out there? It keeps looping it out, right? That giant storm right there. Yeah, that's called a solar flare. And sometimes they're really, really big. And when they're really big, they're called solar disturbance, something like that. And they can mess up our cell phones on those days. If you've ever had a day say, why isn't my cell phone working? Could be solar activity. It also affects the aurora borealis and australis. Yes?
There was a solar storm a couple nights ago.
Oh, yeah? Okay. It probably made really good auroras then. We talked about
Oh yeah,
auroras
they
in this
said
class,
they
right?
said you can see them down
No?
south.
Okay.
Like down south here,
Oh, this far south?
probably yeah.
Oh, that's one of my things on my list to see. I want to see the aurora. Borealis probably. Australis means the ones down south. Nobody's close enough to those. All right, so take a look at this. I like this. So this looks like a little fan, right? Okay, but let's start here. Look at the waves. All right? So at the beginning, the waves are big and fat. Then they get skinny, skinny, skinny. All right, look right in the middle of that rainbow. Right in the middle right there is the visible light. Now let's look what they're called. Microwave, infrared, visible, ultraviolet, X-ray, gamma at the end. So the shortest waves are the gamma rays. Anybody ever watched like I don't know, Star Trek or whatever? Gamma ray gun, right? They're going to shoot you. If we really had gamma ray guns, they would just burn a hole right through you. because gamma rays are that dangerous. They're coming from the sun right now. But guess what? The atmosphere is, and the magnetic field of the earth is deflecting them. Boom, boom. It's like we have a magic shield around us. All right? But all these waves are coming in. The X-ray waves, right there, we use those in medicine, right? We use this in medicine to take X-rays to see inside the body. All right, so it's pretty cool stuff. All right, the next one, sound energy. It's mechanical energy. So mechanical energy, of course, means something that's moving. That's all that really means. It's moving, and it's making something move. That's the mechanical part of it. So what's moving right now, y'all can hear my voice, presumably. Yeah, you can hear my voice. I am sending energy waves through the air, and they're going down in the little funnel right here called your ear, and making something move. Like this. Your eardrum is vibrating. And that vibrates these little bones, and those little bones vibrate this little thing called the cochlea, and the cochlea vibrates the fluid inside there. And our brain can figure out what y'all can figure out what I'm saying. Okay, so we're going to have a unit on this, a module on this. So we'll study that in more detail then. Nuclear energy. Nuclear energy is something we can use. It's the most efficient form of energy to provide, like say if we want to get lights in our homes or something like this. This is the best way. People are afraid of it because it does end up with some, what do you call that?
Pollution.
The pollution, what do we call it? Nuclear, the stuff left over is radioactive waste. It's radioactive waste is what it is. But it turns out nuclear energy, there's two forms of it. One of them is called fission. Fission is what we use to create power in a big power place to send power to our homes, okay?
A nuclear power plant.
A nuclear power plant. That's not how we get our electricity here, but there is a really big one down in South Texas, a famous one, that is creating energy for the southern part of our state. Fission means to take apart, And what we have is we have a large atom that is naturally unstable. It's an atom that's wobbly. It's got too many neutrons in it, or in some cases too few neutrons in it, and it's unstable and it wants to fall apart. It wants to break into pieces. All right, so if we shoot something at it, we can control that a little better, okay? And when we do that, we can get these things splitting apart, giving me a new particle, alpha particle, gamma particle, beta particle, one of these particles, which causes motion, which causes heat, which will boil water, which will make steam, which will turn a turbine, which will turn a magnet around a wire. Voila, I have electricity. That's how it works. If I can find a way to boil water, I got electricity. That's all I need, boil water. And that's how we're doing right here. So it releases energy by splitting atomic nuclei apart. So that's breaking the nucleus up. That's physics. Chemistry, we can't break up a nucleus unless it's radioactive, but they don't sell those to me. They don't sell me radioactive stuff. It tends to make people sick and burn your hands and things like this. And chemistry is only about messing with the electrons, changing the where the electrons are. That's chemistry. Yes?
So if the electricity went out in my house, I could boil water for fire and get electricity?
If you had a turbine with a magnet that went around a wire, yes. You got to have a way to generate it. Okay? So in other words, if you had like this, it's just like a big spinning thing, like a fan, and it spins. So like think about this. If you have, next time you have a fire, if you come up close to it with like a little pinwheel thing, the heat of the fire will cause it to turn. All right? So that's energy right there, right? If I can harness it, then I can get energy from my home. The hard part's harnessing it and controlling it, right? All right, so nuclear energy can either be fission, which we do in a nuclear power plant, or nuclear fusion. Now this is more difficult. If I take two small atoms and join them together and make a whole new thing, I have what's called fusion. I'm fusing them together. We think this is what's happening in the sun. We're pretty sure that's what's happening. They get crushed down. Hydrogen atoms get crushed down so close to each other with all that immense pressure and heat, and it causes them to meld together and become helium. And when that happens, it goes from one proton inside the nucleus to two protons inside the nucleus, hydrogen to helium. We have not figured out how to do this on the planet Earth. There has been something that comes close called cold fusion. We have to have it at like negative 400 degrees in order for it to happen. And so then they've discovered something. They said that, you can't have this conductivity unless it's negative 400 degrees. Then they found out there were some things that could do it at negative 300. Ooh, those are called semiconductors. But it's still
Learn
very
about
cold.
that.
It's still very cold. You read about that?
Yeah.
Semiconductors?
Was that in Model 7?
That has to do with nuclear stuff, messing with the nuclei. All right, but this fusion thing, if y'all could figure out how to do fusion, controlled fusion, without it turning into something as hot as the sun, that's very hot, then you could be gazillionaires. Because we would have power, you know, just think, if all I need is hydrogen to make helium, to make all this power, wow. The problem is it becomes as hot as the sun. And that burns up all the containers that we can hold it in, right? So, boy howdy, that's tough. But the idea here is we're using the radiation energy of the sun to capture it in those cool, you know, what do you call those, solar panels, and try to translate it from a solar panel. So you heard of solar energy, right? It's just not quite where it needs to be. In a place like Texas, it's a little better because we have a lot of sun most of the year. But I have a sister-in-law who lives in Michigan.
Oh god.
It's like cloudy every day. And they couldn't do as well with solar energy there. It's always cloudy. You like cloudy?
I like cloudy.
Oh, I like sunny. All right, so here we go. Here's our fission. We have a large atom that's unstable. We shoot a neutron in it just to get it started. It does it naturally. But to get it started so we can control it and use the energy, we shoot a neutron at it, and it breaks up from uranium-295 to uranium-236. It sends out these little particles. Some neutrons or neutrinos at this point, and then we have a krypton and a barium. So 2 new atoms coming out that way. Here, nuclear fusion, we take something, this is called heavy hydrogen, deuterium, and tritium, that's also hydrogen, and we turn it into helium plus a neutron. Except we can't do that. We haven't been able to do it in a controlled situation. Okay, next we have the law of conservation of energy, and this is that energy is neither created or destroyed, it only changes form, right? It only changes form. If I have energy or power from something or work being done, it had to come from somewhere. It can't come out of nowhere. All right, that breaks the number 1 law on the planet, which is the first law of thermodynamics, also known as the law of conservation of energy. Then we could actually add mass into it. Mass is neither created nor destroyed, it comes from somewhere. I can't just, you know the magicians who make something disappear? They've just tricked you. Because it can't just disappear. It went somewhere. Even in a chemical reaction, if I'm burning a candle, you still want my candle to disappear. Yeah, but it went off as light, heat, smoke, ash, melted wax. All right, it all got translated and changed into a different thing. Yes.
I have a quick question. It's like, what if you, like, you know, there's bowling. What if you threw a bowling ball at someone on the moon? Would it still be super heavy, or would it heavy?
It wouldn't be as heavy
Oh.
because of the gravity of the moon.
Would
Okay.
it still hurt?
I would think so.
It wouldn't go very far because you
I think
throw
you
it.
could probably
Would
throw
it?
it farther.
Yeah.
It probably would be the same ratio of heaviness for you, because you'd be lighter. So it would be lighter too.
Maybe.
It would still feel just as heavy.
I just know I've seen an astronaut drop 2 things like this, and they fell kind of like slowly.
Mm-hmm.
Yeah. Yes.
Humans have energy, right?
Oh yeah.
So
You can
if
see it
humans
thermally.
Die.
Yeah. What happens to the energy? Okay. Well, it gets recycled. Because what happens to your body?
Decompose.
Oh, it's kind of nasty.
And all that stuff gets decomposed. Some of your body gets reused right away if you donate your organs. Those will get reused, right?
Sick.
So the bigger question is when you're looking at stuff like spiritual or soul.
Yeah.
What about that? Where does that go?
What is that?
I would say it's eternal. Right, it's eternal. Heaven. Hopefully. Yes.
My parents are gonna cremate it, and whenever they both do die, they want to release them in the same spot. So they go.
Okay. There you go.
Yeah.
That's once you're dead, your body is nothing. It's
Yeah.
meaningless. Yeah. So, yes.
But yeah.
I think I'm just gonna keep my skeleton.
Yeah.
Okay. For your grandkids and stuff to say, oh, there's old grandpa. John
I want to
Marks.
be put in what's it
Put it
called?
in
You
like
know,
this.
you know, just
Cryogenic.
No,
Yes.
like,
Hang yourself on the wall.
What's
This
that thing where they
glass
put like
case.
animals in that liquid?
No, you'll be like a
Oh,
on-
taxidermy?
on the
No
wall.
floor.
Your kid-
Formaldehyde.
your
I
kids-
want to put it in a tank of
Hi, Dad.
formaldehyde.
Yeah.
Just like.
Yeah, that'd be really
That'd
creepy.
be good.
People do that. I've heard of it. Okay, so energy is only transferred. So in this particular picture right here, we see the bowling ball going and hitting the pins. And so the ball is stomping a little bit. The pins are, of course, getting scattered, right? So that energy is being translated, it's being transferred from the ball to the pins. All right, work. Now, open your books up. This we're gonna have some blanks to fill in. I wanted to cover that stuff first, but now we'll be filling in some blanks in your book. What does the physics term work mean? You remember that from last time? Remember what it means?
Moving.
Yeah, something had to move. Okay, this is the question I did last week. Is there any work done if I push against the wall and it does not move?
No.
No, not against the wall. There's no work done to the wall. Is there work done to my muscles?
Yes.
Yeah, I've been moving those. You know. All right, let's watch
What's
a
the
little.
page?
My muscles, see?
What page are we on?
What page
67.
are we on?
57.
I'm moving my muscles, dude.
I don't think there's a blank yet to fill in. Is there? Let's watch an introductory video on work.
It's about.
Wait,
The blank is
wait,
about
wait,
work.
Okay.
Are we supposed to read the blank?
We're not there yet.
Oh.
Oh, this is very violent, the beginning of this video. Yikes.
Hey,
I know, it's
That's
it
hard
keeps
to
going.
watch.
how do they do that?
And now,
Movie magic.
It looks like it's movie magic. It's like for real.
I think it was real.
Oh, there's no one in there.
For real.
It's kind of like a cinema.
As dogs pull a sled through the snow, work is being done. Work is defined as the product of the force and the distance over which the force is applied.
We knew that.
And since the work involves a transfer to energy, the units of measurement are joules.
We knew that.
Let's say that the dogs are applying a force of 700 newtons to the sled, and they pull the sled for 900 meters. We can calculate the amount of work being done. Substituting values for F and D and multiplying them together, we find that the work that the dogs are doing is 630,000 joules.
I don't believe.
Oh.
That's a lot of work.
When a plane lands, work is done to bring it to a stop. Force is applied to the plane to slow it down. Through the friction of the wheels on the ground, the friction on the wings, and, in extreme circumstances, hooks and straps to bring it to a rapid stop.
That's how they crash test cars.
That's what they're doing.
That's a pretty good car.
Another example is during a car crash. Work is done on the car, causing it to stop.
All right, so that was work. Here's our first blank. Energy is defined as the ability to do work. Work is the product of a force. That's the word you're writing in that blank, right? The product of a force applied in the direction of motion of an object and the distance the object moves. It has to move. We good? All right, so let's see here. Who has done the most work? We're looking at two scenarios here where people are pushing giant boulders. This one's really big, and the guy's not strong enough to push it. So he pushes against it, it doesn't roll at all. So he's pushed it 0. So it's 500 newtons of force against it isn't enough. So 500 times 0 equals 0. How much work was done? 0. Over here though, this guy's able to push this 1,000? 100? 100 kilograms. And he uses 500 newtons of force. He pushes it 6 meters. 500 times 6, 3. Is that 1,000? Joules. 3,000 joules.
So work is only done using distance.
Because it has to move. It must move. All right? So therefore, the product of a force and the distance the object move. Okay? Of course, notice we knew the force was 500 newtons. So they had to get that to us. That's calculatable, but it had, in this case, it was given to us. All right, work. Work is accomplished when two things happen. One, the object has to move. Like this box. This guy's picking this box up. Looks like he's using good box picking up technique by using his legs. Because if you bend down like this and pick it up, you're going to hurt your back.
Do we write that down?
I don't know. And a force must be acting on it.
I think so.
But sometimes that force can be, gravity. So work is done to this box. The man does work on the box as he uses a force to lift it a distance. He is lifting it against the force of gravity. If he dropped it, gravity would be, it'd be in free fall, right? The sole force would be gravity. All right, we're going to say the same thing here. Work is accomplished when two things happen. Object must move and the force must be acting on the object. So here we're looking at pushing a box across the floor in the same direction. So we have something working against it, which would be friction, right? As long as we keep it moving, we know that. It also depends on direction. Notice when it said about that plane stopping, that's another thing too. We have acceleration, we have negative acceleration, right? In order to slow something down. That's still work that's being done. Because there's motion, it's motion going against, just like we did those word problems on that. All right, so there they are. We see work being done. We have an equation. You're supposed to write this down in that
There you
box.
have it.
It's already written down for you?
Yeah.
Oh, okay.
Oh, really?
Work equals force times distance. The unit of force would be in newtons. The distance should be in meters. Sometimes they'll give us a problem that we have to change into meters. Maybe it'd be something easy like kilometers into meters. That's easy.
So,
But feet or miles into meters, yikes. We have to do some more work on that. Yes.
you can't do the equation unless you have meters.
I think you could do it if you did everything in the English system. For instance, you could do miles per hour, right? So miles and this is newtons. That's still force. Our force would be something besides newtons.
Yeah.
What is the force in the English system? Like pounds or something, pounds of pressure or something like that.
Yeah.
So I think if we're using newtons, we have to stick with meters
Okay.
because newtons is in the metric. Okay, so here's an example. Do you have a box to write an example down? 8.3.
Yes.
All right. You lift a book from the floor to a bookshelf that is 1.5 meters above the ground. You exert 19.6 newtons upward force in lifting the book. How much work did you do? What are we going to do?
Not a lot.
Not a lot of force? Okay. What do we start with? How do we begin this problem?
We write down our known.
Write down what we know. Right? We know that we're lifting something. The distance is 1.5 meters, right? So we know D equals 1.5 meters. And then we also know the newtons, so we know the F force is 19.6 newtons. It is telling us upward there, vector quantity, right? So then we know what is our formula? Here we're writing everything. We're looking for W. So we have F from there. We have D from there. We're looking for W. Who remembers what we have to do? It's not hard.
Multiply.
There it is. W equals F times D. We plug those numbers in. We put it into our calculator. Yes, you may use a calculator. I'm going to be sending this quiz home with you. You can use your notes on this at home. Okay, and you can definitely use a calculator. Okay? All right, so 29.4 Newton meter equals, remember what Newton meter is. A Newton meter is a joule. All right, because work's been done. So our final answer is 29.4 joules is how much work was done lifting the book that distance. That's good to know, right? I don't know. Do we really care?
We're almost done.
What?
Sometimes with math problems, I'm always like, do we really care? Who cares?
Okay.
Pick it up and put it in the bookcase. I don't care how much work it takes. If my kid said, that's too much work, I said, no, it's not. It's only 29.4 joules. Very little amount. Okay, we're going to be back to the girl on the books here in a minute. But here, power. So what is power? More power, right? Power is the amount of work done each second. What are we bringing into it now? Time. We're bringing time into it. How much work, which we know how to calculate work, per second, which is going to actually bring us to a new unit. A unit that takes the joule and adds some time to it. Okay, so we're going to have a new one. It's pretty cool. Power is calculated by dividing work, which we already calculated, by time. So how long did it take this girl to lift that into the let's say it took 1 second, so therefore it'd still be 29.4, right? Because over 1, right? So here we have power equals work, which we realized from the F equals, work equals, let me write that down. Work equals F times D, right? And now power equals W over time in seconds. And the unit is called a watt.
I've heard of that.
Somebody say what?
Kilowatt.
Say what?
What?
That's right. A watt. What is watt? What is watt? It's a joule per second. A watt is a joule per second. So there it is, watt. Now where do we get the word watt? When you hear about watts, what do you think about? What?
Electricity.
Yeah, but what particularly?
Light bulb.
Light bulbs. Yeah. So, like a 60 watt light bulb. That means it's burning 60 joules per second.
TJ, what?
It's definitely named after a guy.
Dr. Watt.
No, it's a focal point.
So here we're looking at work versus power. This guy, excuse me, digging his snow versus using a snow, what's that called?
Snowflower.
Yeah.
That's
a
a lot of
snow.
work.
This is a lot of
Oh.
work.
It's
Yeah.
called the snow blower.
I'd rather shovel it.
Snow blower, yeah, okay. All right, let's watch this little thing that's gonna compare this. And the way they compared this on here, I've never thought of it before. Okay, I've never thought of it this way, so it's really cool. Also, for Christmas, I got a grandfather clock. And it's really, it's like a 100-year-old grandfather clock.
Dang, where'd they get it?
Well, we have a friend who's really into clocks. And he said, you want me to help you find a clock? We're like, okay, so he helped us find a clock. That's Mr. Wilkes, you know Mr. Wilkes? He loves clocks from church.
You said clocks way many times in that sentence.
Too many using clocks. Now the word sounds fun. Okay, so watch this. Okay, clocks.
In physics, the concepts of work and power help us understand and explain lots of things in our universe. Let's start with work. Positive work is the energy we put into a system, and negative work is energy that's transferred out. Think of positive work as money being added to your bank account, and negative work as money taken out. In the metric system, work and energy are measured in joules. As an example, let's take a beautiful old mechanical grandfather clock. We transfer energy into the clock when we turn the crank to raise the heavy metal cylinders inside the clock. When we do this, we're doing positive work, adding energy to the clock. And that energy is stored as gravitational potential energy. We can calculate the amount of work done by multiplying the force we apply times the distance over which we apply the force. To raise the metal cylinders, we need to apply a force equal to their weight. That is, equal to the force of gravity pulling downward on the cylinders. These cylinders weigh 300 newtons, which is pretty heavy, about as much as a small child. And if we lift them 1/2 meter, then we do 300 newtons times 1/2 meter, or 150 joules of work. Power is the rate at which energy is transferred. When we say rate, we mean the amount of energy transferred per unit of time. In the metric system, power is measured in joules per second, or watts. The term watt goes back to James Watt,
There he is.
who came up with the concept of horsepower to measure the amount of power produced by a typical workhorse. James Watt was a producer of industrial steam engines, and he wanted his potential customers to be able to make comparisons between his steam engines and a familiar quantity, the power they could get from a working horse. This was such a useful idea that the metric system unit for power, the watt, is named after James Watt. Following in James Watt's footsteps, let's compare the amount of power it takes to run this grandfather clock to the power we'd need to run a bright 100-watt light bulb. We can measure the power a person uses to wind the clock by dividing the amount of work they did by the time it took them to do it. If it takes 1 minute or 60 seconds to lift the weights, then they are doing 150 joules divided by 60 seconds, or 2.5 joules per second of work. They are adding energy to the clock at a rate of 2.5 watts. you'd need about 40 times as much to run a bright 100-watt light bulb. Before we let the clock run, the energy is stored as gravitational potential energy of the cylinders. It's like your bank account when you have just deposited money. But if we let the clock run, the cylinders slowly move downward. Energy is leaving the clock. In fact, when the cylinders get to the bottom, all the energy that we put in will have left. So how much power does the clock use? That is, how many joules of energy per second leave the clock if it takes 5 days for the cylinders to return to their original position? We can figure this out because we already know how much work we did when we lifted the cylinders, 150 joules. But this time it took 5 days rather than a minute. 5 days is 5 times 24 times 60 times 60 again, or 432,000 seconds. So we divide the work done by the time and find an answer of about 0.00035 joules per second, or about 0.35 milliwatts. That's a tiny amount of power. This clock uses so little power that you could run almost 300,000 clocks using the same power it takes to run one 100-watt bulb. That's right, you could run a clock in every house in a medium-sized city with that much power. That's a pretty amazing conclusion, and it took knowledge of work and power to figure it out.
Okay, pretty cool, huh? So I have this this grandfather clock, and sure enough, it's got those weights. And there, you know why there's 2 different weights? One's for the hour hand and one's for the minute hand. And the one for the hour hand is heavier than the one for the minute hand. I never thought of that before, you know. But I remember when the guy came over to set it up, he said, "Oh, give me the heavier one." You know, I was like, "Oh," and it was very heavy, and I handed it to him. So I have to wind it up, right? So what I've noticed about my grandfather clock is that if the weights get down about, and they kind of go at a little different rate, they're not always equal because the heavy one's heavier, right? So they go down. When they get about not even halfway down, it keeps time. The time's going, but it stops chiming. You know how it chimes like dong, dong, 2 o'clock, right? You know, it stops chiming. So I asked my clock friend, I said, why does it stop chiming when it's just here? You know, it's not like the clock stopped. He goes, I don't know. So it's just one of those idiosyncrasies of my clock, apparently. So I have to wind it a lot, like every other day, if I want to hear the chimes. One time, I went in, because I hadn't heard the chime in a while, and my weights were way down here, and I wound it up and everything, and it was good and everything, but then I realized it wasn't keeping time at all. So in other words, I let all the energy power run out of it. And I felt like an abusive parent. So I had to start it, but you know how you start it, right? Had to push that pendulum and just get it going again, you know. So anyway, it's just all operating off of gravitational pull, which is pretty cool stuff. And notice when we talked about power, how much it would take to versus put power as a light bulb. Think about that clock. It's keeping time. It's not plugged in, right? It's strictly using the power invested in it by my winding and gravity pulling those down. Pretty cool.
How does it keep accurate time?
Well, I will say it's really decided that it wants to be 3 hours late. Excuse me, 3 minutes late every time. I move it and I change it to the right time, and the next thing we know, it's 3 minutes late.
So
You said 3 hours.
Try to make it
It's 3 minutes. 3 minutes.
Try to make it 6 minutes early.
Like early, I could try that
So
and see if it catches up. Yeah,
if that was your only clock,
I'll trick it, right, John Mark? I'll trick it.
how would you know?
That's a
in
really
this
great. We don't know. We've asked that question too.
Why
Like, well,
would
if we didn't have another timepiece to, how would we know? You know, because in the old days when that's the only
The
kind of
big
clocks they
clock.
had, it was very important to remember to wind them. Right now, if I forget to wind it, I'll just reset it.
But you used to have the town clock.
That's true. They had the town clock. Maybe a sundial, something like that. All right. Here we go. Now we're going to take that book again, and we're going to ask now how much power it took, not how much energy. Is that what we said before? Not as many joules, but now we're looking for watts. And by the way, Mr. Watt, James Watt, I'm pretty sure he invented the steam engine. Does that sound right? Somebody know? He's a British guy. I think he invented it, the steam engine. Okay. You lift a book from the floor to a bookshelf. Oh, it's 1.8 meters, a little higher, above the floor using a force of 16.5. You lift the book to in 2 seconds. How much power in watts do you use? All right, so the first thing we have to do is find out what our work is, right? We got to do that part first, because then we'll plug it into the power formula. Here's the girl lifting the book. Okay, so we know our force is 16.5 newtons. We know our distance is 1.8 meters. We know our time is 2 seconds. What is our power in W? So we're going to start here with this one and then go to this one. Oh, we can rearrange and do this. P equals F times D over T. We can write that one down. It's saying the same thing, you know, it's just putting these two together. So P equals F D over time in seconds. Or we could do 2 steps. We could find the W first and then plug it in. All right, so we're going to put all those in like that, and we're going to see, after we do the work here, the Newton meter per second, the joules per second. Remember that Newton meters, joules, and then we have the second. So joules per second is what? That was the clue. Joules per second is what?
Watts.
There you go. What?
What?
What? Right.
What do you?
Right.
What do you mean?
That's exactly what I mean. 14.85 watts.
Don't
So
worry.
what's the difference? Earlier we did a little bit different problem, but we were finding out what the work was done. Now we're finding what power it took to get that work done. Finding the power involved in it, okay? So you get the difference? What? What? Do y'all need to write this down? Are you still writing? Okay.
I ran out of room, so I just looked at it.
Keep in mind it is in your book.
Oh,
You can find it in your textbook. In the old days, the textbook had them like in a big purple box. I don't know if it's still the purple box now.
So you divide the
They're in a
work
brown box
times the
now.
time?
F times D divided by T.
The box is a light brown color.
It's light brown? Okay.
Well,
So in the light brown
look,
box,
it's Gracie picking up
the
my book.
textbook.
Oh,
Have you not seen the textbook? My hair's not long like that.
I know.
Hopefully y'all are reading the textbook. So
I'm reading it.
I hate that.
Alright. you are. Okay, good. Good. I'm happy to hear that. If you're not, then I'm not doing well here. All right. A girl runs up a flight of stairs in 2.6 minutes. If the work she has done is equal to 320 joules, how much power did she use to climb the stairs? All right, so what do we have here? We have the work, W, and we have the time. There's a problem with the time, however, right? It's in minutes. I think we need to maybe, let's see if we have to convert that to seconds. Here she is running up the stairs,
Oh
and
my
as
gosh.
a matter of fact,
Whoa.
yeah,
Zoe.
our lab today was supposed to be us running up some stairs.
We don't have any stairs around.
There's no stairs here, so I had to come up with a different lab.
I
But
get
in your book, if you want to do that lab,
Running
you
upstairs.
have to
actually
weigh
pretty easy.
yourself, and you have to carry something up the stairs.
human stairs, and we run up to people. Like that.
We have
you know,
stairs.
Dangerous
No,
to
no, no,
run
no,
up
no,
yeah,
wait,
go
you
away,
have
people
a
are
pyramid?
talking.
Human stairs. Okay.
Human stairs, and we run up to people.
Okay, y'all want?
Makeshift.
So do you climb up you like stairs?
No.
No.
No. Yes, Ross.
Running upstairs is actually quite easy. I've done it before.
See, an athlete would say that. A grandma would say, "Oh,
Yeah.
no."
Wow.
Okay.
Grandma?
I'm a grandma. I'm talking about me.
Oh, really?
All right. So we know our W is 320 joules. We know our time is 2.6. What is our P, our power, in watts? So here it is. We do have to transpose the minutes to seconds. So we know, how do you do that? How do you convert? You take what you know and you put it over 1, 2.6 over 1, and you say how do they relate to each other? 1 minute has 60 seconds. Make sure what you're trying to get rid of, the minutes, you want one on the bottom and one on the top, then you can cancel those out and end up with the unit that you want here. In this case would be the seconds that we want. Okay, now we can plug everything into this thing right here. So 320 joules divided by 156 seconds gives me 2.5 joules per second, which is what?
Watts.
Watts. 2.05 watts.
Oh, I was supposed to know.
That's your answer. Typically you
This
like
is
to have the answer in.
This is
Put a box.
2.05.
Are you, oh, it's both 2.05, right?
Yeah, that's what I got.
2.05, 2.05.
No, it's 2.0512820051.
Oh. Well, we have to
That's
we
where
have to pay
you're
attention to significant
wrong.
figures. The laws of significant figures state that we have to stop at 2.05
Oh.
because this number was only 3 months long. But you don't want to deal with significant figures. It's a pain.
I don't want to.
It's annoying. Even in my classes that we have to deal with it, I'm like, ugh, let's ignore it.
I don't know. If
My chemistry class.
significant figures are.
I know, it's silly. It has to do with the number of numbers, the number of digits that are in there. There's 2 digits, right?
Do you learn
This
that in
has
algebra
three.
too?
You learn it in physics and chemistry.
Oh.
I don't know about algebra 2. All right, machines will increase our force.
Yay.
They will give us something called leverage or leverage.
Canadians there.
All right, so here's a machine. What does this machine help us do?
So,
So, yeah, make
Things
clothes.
together.
If you had to make a shirt for yourself, would you prefer to have a sewing machine rather than just needle and thread?
Yeah.
I would
Mhm,
rather
me too.
just not wear.
Me too. I'd rather just pay somebody to do it because I'm no good at this kind of thing. My sister's really, really a good seamstress. I'm terrible.
We're neighbors with someone who's really good at sewing.
Yeah, I'm not good at it. Oh, here's some of the things these are some of this is what I could use instead of this, right? So this makes this simpler. Notice I still have machines over here. I have scissors. I have a needle. Those are machines too.
Are those a machine?
Oh yeah.
Yeah.
Yeah, because it's got a little point on the end of it.
It's a simple
What machine is it?
Sewing machine.
Lever.
No. Y'all know this.
Screw.
Wedge.
Wedge is correct.
Right. Almost.
All right, so here are the simple machines. We know them, yes?
Yes.
So here is the screw.
Yes.
What's this?
Wheel.
Pulley.
Pulley,
Wheel and axle.
wheel and axle,
Wedge.
That's
Incline plane.
incline
So-
plane. Here's your wedge
so-
over here, David, right here.
I was gonna say slope.
What's this?
Lever.
Lever. Here's another lever down here.
Yep.
If we look at the door, we have a wedge under the
Wedge.
door here. That's a door stop. That's a wedge. Our
Incline
door
plane.
also utilizes the wheel and axle with the doorknob. You could even say the door itself could be an incline plane if you wanted to use it that way. I don't know what those flags are supposed. Oh, they have a pulley on them to pull the flag up. That kind of thing. All right, machines and mechanical advantage. Those of you who were in my general science class,
I was
remember
there.
that.
Yeah. I feel like I just learned this yesterday.
We did not care for that. Remember, we had to do those. That was when we had math
so
and
annoying.
general science, and we had to do all those mechanical advantage formulas.
That's fun.
Machines help us do work. There's a blank to fill in. Work. So, for instance, we see a simple machine right here. It's called a hammer. Okay, the hammer is a lever.
And a wedge.
Best machine in the world.
It could maybe consider the back part of it there a wedge, but it's also a lever as well. So we have work input and work output. So the force you apply to the hammer and the distance over which you apply that force is the input force and the input distance. The input force and output distance are the force the hammer applies to the nail and the distance through which the force is exerted. Input force is the force applied by the person on the machine. Output force, that's a blank to fill in, is the force exerted by the machine. Input distance is the distance to input. Distance to input force? That doesn't
So
make
the
sense.
input distance is the distance.
They
input
could have put the
force.
two
That is
next to
kind of
input.
redundant.
We have the right thing.
Output distance describes the distance the output force is exerted through, or how far the load moves. The load being the nail at this point. So what did we decide the sentence is supposed to say? Input distance is the distance to input force.
Yeah, that's
And
right.
take the is out? Is applied? That sentence doesn't make any sense to me.
Input distance.
That's what's in the book I wrote.
Is the distance to input force. Oh yeah, that doesn't make sense.
No, it doesn't. So I think we should put the period right after force. Input distance is the distance to input force, period.
Or input distance is the distance applied.
Or stop saying distance
Yeah.
and input so much.
I know. It's annoying.
Distance.
All right, I apologize for that. That's what's in your book, however. We need to
Apply.
report that to the book writer. All right, machines and mechanical advantage. We can calculate the actual mechanical advantage of a machine. This is a little bit different. It says AMA, I guess actual mechanical advantage. We just talked about MA, mechanical advantage, in general science, which has now been removed. I don't know if y'all knew that. It's been removed. All that whole simple machine thing's been removed from general science, and they put it in physical science.
It doesn't make sense.
All right, there it is again. So the actual mechanical advantage, output force over input force. The ideal mechanical advantage, IMA, means if there were no other things affecting it, gravity, friction, whatever. Input distance, output distance. So actual, I'm guessing, would be a little more accurate. Okay, an example. A ramp is a simple machine known as an inclined plane. That looks like a misprint to me as well. Shouldn't it be inclined plane? Not inclined plane? I think it's inclined.
Yeah, it's inclined down there.
Inclined, yeah, I think that's a misprint. It's missed in there. A moving company uses a ramp on its truck to help load heavy objects. The ramp is 2.74 meters long. The input distance represented by the red arrow on the ramp diagram. The ramp is used to lift the boxes a distance of 0.91 meters. The output distance, that's the yellow arrow right there. What is the IMA of the inclined plane? So does anybody remember that formula? I didn't write it down.
Input over output.
And it was called the IMA.
Yeah. Is IMA ideal? Or,
Yes.
Yeah. Ideal.
Oh, it's a lot of math formula. Okay, input distance, output distance. We need to make sure that's distance. Okay. What's the IMA? Do we not have it? Are
We
we
do.
continuing here? Okay. 2.74 meter over 0.91 meter equals 3. The effort exerted by the man is 3 times less when using the ramp than if he lifted the boxes from the ground to the truck. The trade-off is that the input force must be applied over a greater distance than if the boxes were lifted directly onto the truck. Okay. Wasn't the MA of a ramp something about the slope? You know, the height divided by the
Yeah.
slope or something? Remember that from general
The table's
science?
on a slope, what?
You would have to know the slope at that point.
It
You
would
would have to
lift
get
off
rise
on
over
the
run
side.
and then
Whoa,
It
oh,
does
it
it
goes in.
Slope divided by height. I think.
Huh?
Or is either slope divided by height or height divided by slope?
One of those, yeah. So
Well,
this
yeah.
just,
Z,
this,
did you say
we
all
just
that?
have to know which distance is what
What is
distance.
that?
Seems a little more confusing to me. If you exert, guys, if you exert 95 newtons of force on a jack to lift a 9,500 newton car, what would be the jack's actual mechanical advantage? The AMA. All right, so we see somebody lifting a car. But we're not lifting a car like that.
His legs are
We're
so
lifting a car like that.
Oh, lot.
I don't know if you've ever had to change a tire before, but
Nope.
it's really
Never
nice to have a
happened.
jack to jack the car up.
I just pick it up.
I just picked it up.
All right, input force 95 newtons, output force 9,500 newtons, which is against. That's the force against the input force. What's our AMA? We just do some simple math right here. We find out.
Simple math.
In finding AMA and IMA, the units will always cancel out. Notice there are no units associated with that. It's just 100. 100 what? Just 100. Wasn't that interesting? Notice how much larger the AMA of the jack is than the IMA of the ramp. I don't think those are very good comparisons.
Terrible.
That's terrible. Yeah. So, I didn't write the book.
I'm very tired.
Oh, yeah.
Shit.
All right, efficiency. Friction acts on input force so we can calculate the efficiency of a machine. Work output over work input times 100%. The percentage of work input that becomes work output is the efficiency of a machine. So we have we don't have an example for that one.
Oh, shoot.
Good thing, right? Let me check their quiz here real quick.
Should we memorize these formulas?
You know what it says here? It says you're supposed to, you can have yourself a little card, a little formula card.
Oh no way, for real?
Yeah, and that means you can have it for your, almost.
For the midterm?
You can have it for the midterm.
Yes.
So go ahead and just tell me here, you can do like a 3x5 card with your formula on it.
Hey! It's not cheating if she says it's not.
They say it here. It's not me. I could change it, I guess.
No.
All right,
No,
when you
no.
when you look in your textbook, when you're reading through Module 8, you'll see at the end of the module on page 302, there's this pretty handy dandy nifty little, what do we call this, scientific infographic. And it's showing all of the simple machines. How many simple machines are there? 6. 1 inclined plane. 2 the wedge. 3, does that say pulley?
Pulley.
Pulley. 4 wheel and axle. 5
Lever.
lever. And
Lever.
6 the screw. All right, so they'll show that. So you see here they are. This is just bringing it a little bit there. The 6 types of simple machines.
I know this is gonna be on the test.
And that may be on, it doesn't look like it's on the quiz, however. Oh wait, maybe it is.
It was on the test last year.
Yeah, list the 6 simple machines, right on.
Lava.
Alright, lap time.
Wait, go back. I
Hold
need
on,
to
hold
put
on.
that in.
Oh, there.
Thank you.
You're welcome. Okay, so I'm gonna go ahead and hand you this. This is your take-home quiz. So don't forget to give it to you. Remember, studying quiz. Remember, you can use your notes on this one because I won't be able to correct it, right, and give it back to you. So make sure you know the answers on this.
Do we get like the grade on it?
Yes, if you bring it back. So next week when you come for the midterm, bring this with you.
And it gives me extra points.
If you did your study guide, well, you'll get 110 on it if you do your study guide. You'll get 100 on it, presuming you actually answered everything correctly.
Extra credit for doing
Oh, where can I find the study guide for the midterm?
Using your old quizzes.
Oh, so there's not like an actual study guide?
No, not that I know of.
We get extra credit doing that.
You can write that on there. You did that for your last
I'm not
time.
gonna text him.
That's
I
it.
did.
Fine.
There's no midterm.
No. Never mind. We're done.
There's no midterm. Okay, yeah, no midterm review. Sorry.
Oh,
Go over your old quizzes and stuff. Okay.
Guess what?
Go ahead and stop this.
It's